Now, I already have a movie for this, but I want to make another one because last night at my son's hockey practice when I had nothing to do, I went over the PowerPoint and I noticed there was, again, a lot of extra wordy blah, 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 blah. So I've cut most of that out. So we're going to get right to the heart of it and hopefully get through this in good time. So, again, just a little reminder of what intermolecular forces kind of manifest itself as, and really what we're talking about now are physical properties. Okay, so we're not talking chemical properties, we're not talking thermodynamics, we're not talking chemical changes, et cetera, et cetera. Actually, we are talking a little bit about thermodynamics because remember at the beginning when we talked about heats of solution, the energy needed in order to dissolve something, all right? That can be explained by intermolecular forces. So anything that's physical state, melting point, boiling point, how well it dissolves, things like surface tension, right? That's that force that holds a liquid in a container. You know, if you've ever tried to fill a cup or a mug over full with water, you know, you've maybe done that. You're right to the last bit of juice. You know what I'm talking about. Oh, hello. Yep. She was doing announcements, so she's not returned yet. Yep. Okay. Yep. So you know what I'm talking about. You get that last bit of milk or whatever, and you're going to empty the jug, and you get it right over to the top, right? And parents are screaming at you, "Don't spill," you know, and you're saying, "No, I can do it. I can do it." You know what I'm talking about? No, you have no idea. You're just writing. One person knows what I'm talking about. Anyway, that's called surface tension. And different liquids have different surface tensions. Water has a very high surface tension. Those types of properties are determined by intermolecular forces. Essentially, how well can those water molecules hang on to each other to maintain that surface tension? We're going to be making a list of some of these properties at the end of the note. Another property that can be explained by intermolecular forces, and again, these are all physical properties. They don't involve chemical change. Something called vapor pressure. We talked about vapor pressure last year. It's the ability of a liquid to vaporize, to go into the gaseous state. Some liquids are very volatile, which means they vaporize very easily. An example of that is something like acetone or gasoline. If you were to get that on your hand, you may have noticed a cold sensation. It means it evaporates very quickly. That means it has a very high vapor pressure. It vaporizes like crazy. Vapor pressure is determined by intermolecular forces, all right? If the intermolecular forces are very weak, then the vapor pressure will be high. It evaporates very quickly. They're not sticking together very well. So those are a list of some things that are affected by intermolecular forces. We're going to simply talk about physical state when we do our analysis, just for the ease, and I'll talk a little bit more about those other things later on. So if we've got something that's in the solid state at room temperature, in other words, it has a high melting point, then we say that the intermolecular forces are strong. They're being held together strongly, so they're held together in that solid state. If we have, and I don't know why I dropped the right bracket there, if we have medium intermolecular forces, it's potentially a liquid at room temperature. And it has a moderate melting point or boiling point. We can talk in terms of melting points or boiling points. It doesn't matter what we discuss here. I might even, as I'm going along, talk about a high boiling point, and then the next statement I'll say a high melting point. It doesn't matter because they both kind of are related to this intermolecular forces. And if we have a very weak intermolecular force, then we have gases. Okay, so let's define intermolecular force and intramolecular force just to kind of get our minds back onto what we did in the past. You'll notice I just removed some examples and some stuff, some fluff in there, which really is just wasting time writing. as you are writing, in a moment I'm going to be doing some examples where we're going to be comparing Lewis structures, we're going to be comparing numbers of electrons, and we're going to be comparing molecules. And for the sake of speeding up the process, I've got the slides all on a page here for you, so all you have to do is fill it in. And there are 3 pages worth of this, so I'll hand these out as you're writing. And there is, there is one more page, but if you guys already have this one on the end, did I make a mistake here? Nope, that's a different one. Okay, so this is the last page here. 1, 2, 3. You got holes in them all? Yep. Like I said, there's 3 of them. So again, those pages, in a moment, we'll be comparing various molecules. And again, like I said, for the sake of ease and speed, you'll then have those right in front of you, and you can then easily fill them in, not have to worry about drawing charts and all that type of thing. So again, just as kind of a review from last year, intra means within. So intramolecular forces, attractive forces that hold atoms together in compounds. Those are our sigma bonds and pi bonds, right? Example, sigma bonds and pi bonds and all that type of stuff. They hold the atoms together. They're what hold the molecules as a molecule together in one piece. If you're breaking intramolecular forces, you're breaking sigma bonds and pi bonds, you're blowing the molecule apart. We call that chemistry. Those are chemical changes. Intermolecular forces mean in between molecules. They're the attractive forces that are between neighboring molecules. They're broken during physical changes of molecular substances. When it melts, you're pulling apart those attractive forces so that they can move freely as a liquid. When it vaporizes, you're pulling apart any attractive forces there so that they can move independently as gas molecules. They are dependent on the type of molecule. So the strength of that intermolecular force is dependent on whether it's a polar molecule and we've got dipole forces, or if it's a non-polar molecule and we've got London forces. That's what we want to look at today. And intermolecular forces are much weaker than intramolecular forces. And that's really quite obvious. I know it's obvious for me. I've been teaching it long enough, but hopefully I can get this across to you. If you think about it, when you heat up some ice, when you get to 0 degrees Celsius, it simply melts. That means that the intermolecular forces are breaking. If the intramolecular forces were weaker, before it melted, it would have actually undergone a chemical change. You would have actually broken the bonds if the intra were weaker than the inter, because as you heated it up, you would have broken apart the oxygen and the hydrogen, but you don't. As you heat up ice, the first thing it does is melt, and therefore the intermolecular forces are the first things to break away because they're the weakest. All right? If you want to break apart an a water molecule, you need to get up to much higher temperatures, into the thousands of degrees, and then you get to the point where those bonds will start breaking. All right? Okay. And this is just that same picture. I'll bring the whole thing up, and it's worth writing down to just kind of differentiate between. It's the same picture that I would have used last year, or would have had you draw last year. Here we've got an HCl. Oh, I guess we should add one thing to make some sense out of it. Due to the delta En, we'll have a slightly positive end and a slightly negative end, and a slightly positive end and a slightly negative end. I don't have lone pairs in there, but it's not a big deal. And so the sigma bond that exists in between the HCl is an intra. And that weak attraction between the opposite charges of the dipole are an inter. And we're going to be talking about the intermolecular forces today. So last year we talked about ion-ion and then talked about dipoles. And then ultimately we talked about London forces, which I think you recall they are the weakest. We're going to do this in reverse this time just because the analysis to go from simplest to most complicated is easier. London forces are really the simplest type of intermolecular forces. They're these induced dipoles that kind of stick them together weakly. Very weak interaction. So London forces exist between all molecules. Anything with electrons can exert a London force against its neighbor. It primarily shows itself for nonpolar molecules, and that's because it is weaker than dipole-dipole interactions. And therefore, if there are no dipoles, then the London forces will kind of present themselves in such a way that they're the only force holding it together. And we are going to be interrupted. And they fear coming in. Come on in. Come on.
Good morning, Mr. Sanders.
Good morning, elves.
Hello. We have a secretary for you.
For who?
For you.
This is all me? No, this is the class. And what are we doing? I'm delivering for the class?
Yeah.
Okay. Wait a minute. What is this? Oh, that's exciting. Jenna. Jenna S. Sorry, Jenna S. Sorry, Granny again. I thought they were going to distribute them, but that's no fun. And they're making me participate in this joyful season. What kind of thing is that? Sydney.
What?
There you go. Merry Christmas. And Miranda. There you go. Someone loves you. This is fun. We're gonna see who has nobody here. Emily. Emily has like all kinds of pictures and exciting stuff. Where do I go in here? Whoops. Positive Minds. So the Positive Minds Club is distributing these. Whoops. And in the end, someone's going to be left out, and that's not going to be very positive. Jenna, again, I tell you, Jenna, look at that. Positive all over the place here. Jessica. I'm laughing because this is really not a Positive Minds thing. Everyone's sitting there looking at me like a 5-year-old waiting for Santa to come along, and in the end, I'm going to be disappointing people. That's just the way it goes. Kristen. I just was back there. Oh, you think you're going to get 2 of them or something? I already got all 3 of you in the corner. It's a little...
Whoa.
Jenna S. This is crazy. Jenna is going to have to share. That's all there is to it.
Sure. No, can't.
Oh, look at that. Oh, look at this. Me. No candy cane tied to it. What kind of a joke is that? And it says, anonymous, period 1 class. That's funny. It's funny. Anonymous. I'm sure. I'm sure it came untied. It better have come untied. Or anyway. Jenna R. There you go. Where am I? Whoops. Wrong line. Sorry, Hannah. It wasn't you. Jenna. Christian. What's that? No, I'm recording all this. I couldn't edit it out. Whoops! That was mine. It's busted up now. Shauna. There you go. That's fun. Is anyone truly sad? They can have mine. I'm not a candy cane eater.
Is yours broken?
Oh, yeah. All right. That was mildly entertaining. Okay. Let us continue. All right, so London forces. Anything that has electrons will exhibit London forces up against another molecule that has electrons, and therefore London forces are exerted on all molecules. Some molecules can exert other forces other than London forces, like dipole-dipole, which we will see. But in this case, when we start analyzing, we want to compare molecules that are not polar so that we can see the effect of this number of electrons. And it's due to the fact that we have the nucleus of one atom being attracted to the electron, the nucleus of one molecule being attracted to the electrons in an adjacent molecule. So it has everything to do with numbers of electrons. So let's go ahead and analyze this particular situation. And what I'm going to do again, just as I've done with all of this stuff in this particular unit, it's one of the pages, and it's on the bottom because I have no idea how to use a photocopier. All right? So it's on page 1, and it's on the bottom. And I am so lazy that I'm not going to fix it. I will give this out till the end of my career. 10 more years, I'll use the same handout. I don't know. Who knows? Oh, yeah, there's 3 of them there. So this is the first one we're doing. Second one, and where is the third one? Third one is right here. Okay, so did everybody find it? It's at the bottom. It's chaos. I know. That's the way it goes. Okay, so come on, folks, listen up. I want to get through this. So to analyze this, and I'm going to give you a heads up on the test as well. When I ask you to determine whether something has a higher melting point or boiling point, I'm even going to give it to you in a nice box like this so it looks like you're used to seeing it. It's really not the greatest way to test if you really know, because what happens is you just kind of do the steps and away you go, which is fine sometimes, but it's probably better if I were to maybe take the box away. But again, I'm going to systematize it for you. When you analyze to determine whether it's going to have strong London forces or weak London forces, follow the steps that I'm giving you here. When I ask you about something like comparing boiling or how it melts, draw a Lewis diagram so that you can start by seeing whether it's polar or not and how many electrons it has. So that's the type of thing that I need you to do. So for F2, right, F 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. All right? And go ahead and draw all the Lewis structures for those. And you'll notice here they're identical. So the delta En is 0. So type of molecule, we say here that it's non-polar because it doesn't have an overall dipole. Now the next step here says number of electrons. Now this is where it can be slightly confusing because I've had you counting electrons to make Lewis diagrams. And those are the valence electrons. But when it comes to London forces, it's all of the electrons that we need to account for, even the electrons in the inner orbitals. So when I ask for number of electrons when comparing molecules that are exerting London forces, we're not looking for 7, but we're looking at 9. All right? So we're looking at 18 electrons in this structure. Okay? And go ahead and complete the table for the rest of those molecules. They're all of our diatomic gases except hydrogen. We didn't include that one. Or oxygen, but we've got a lot of diatomic ones here. So here we're moving down the periodic table. We're looking at the halogens. Again, they're all nonpolar. I hope you've maybe figured that out already, because they're all diatomic. Again, if you're ever unsure on the test how to draw that, and this one's easy, go back to our standard. Count up the valence electrons, make a skeleton structure, go through all the processes. How many electrons for Cl2? Somebody done that? Yeah. Sorry? Somebody say it? 36? 36? 36 electrons? I can't erase. That's fun. 17 times 2. What is it? 34? Br. 70? And I2. 106. In this case, I'm telling you what physical state they're in so that we can see the relationship. We can see the physical state here as well. Gas, gas, liquid, and then ultimately a solid. Notice, more electrons, the greater the London forces, and therefore the higher the melting point or boiling point. So if I were to rank these from low, and we'll go with melting point up to higher melting point, then down here, the low number of electrons will have the weakest London forces, and it will have the lowest melting point. It will take not very much energy to break that apart. So we're looking at F2 is less than Cl2 is less than Br2 is less than I2. Okay? And if you wanted to add some information, this is weak London forces, and these are stronger London forces. Simply because it has the more electrons in it. And they're all nonpolar. If one was polar and it had a dipole interaction, then that would change things. And we'll look at those examples. Okay. So let's do another one here. In this case, let's compare a series of hydrocarbons that just have increasing numbers of carbons and hydrogens. Remember, hydrocarbons, sp3 hybridized carbon, all pointing off in all directions. These are all non-polar substances. So again, very important that we think it through in terms of the Lewis diagram. C, C, and it can be a 3D Lewis, but it doesn't have to be a 3D Lewis, as long as you can visualize whether we're going to have polarity or non-polarity. We'll do a 3D Lewis. We're pretty good at that, so we can kind of have that stick out there and put in there. This guy stick out here and go in there. And that's going to be H and H and H and H. And again, these are all going to point in opposite directions, and so it is non-polar. CH4 is easy to draw, again, as the 3D Lewis. H, 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 H. Again, it is non-polar because all of those dipoles cancel out. Now, C3H8 is kind of a pain, but it can kind of be done a little bit. The way you do it is you put those on an angle like this, which means then you have one sticking out in front and one going in behind. And here again, you've got one out here, H, one sticking out, one going behind, and then an H out here, one sticking out, one going behind. if you are struggling with seeing something as complex maybe as that 3D Lewis structure for something like a C3H8, don't worry about it. You could just put, the good old-fashioned square, make them flat out there. But that's the way that would kind of look. It's not a big deal if you can't see it and you're not comfortable with that. You could just put it flat. It doesn't matter. The fact that it's all C's and all H's means they're going to cancel out the dipoles, and it is non-polar. So again, we've got three molecules that are non-polar, which means London forces are going to be what's responsible for holding them together. And so it's going to come down to number of electrons. So again, we want total electrons for this. So I've got 2 carbons, but this time it's total electrons. So it's 2 times 6. And in this case, it is 1 times 6. What's that, 18 electrons? 18 electrons. This guy is just going to be 6 plus 4, and that's 10 electrons. 6 coming from the carbon and 4 coming from the hydrogen. And this is going to be 3 times 6 plus 8. And what's that, 18, 20, 26? 26 electrons. And therefore, if we want to go in terms of increasing melting point, right, or boiling point, it doesn't matter, which is going to have the lowest melting point or boiling point of this thing. What's that? Someone other than a veteran. What's it going to be? Yes. CH4 has got the lowest number of electrons. The London forces are going to be the weakest. And so CH4 is less than, what's going to be next? C2H6 less than C3H8. All right? Now, room temperature, all 3 of those are gases, but if you were to cool it down below that, this condenses first, right? This is methane, this is what's called ethane, and this is propane, the same propane that you would burn in a barbecue. Okay, let's now talk about dipole-dipole forces. Anonymous, eh? I could correlate this with the assignments that just were handed in, and I could do a handwriting comparison. We'll just put that with the assignments. Just so I can say thank you. Cheapers. Come on. So if we have polar molecules, then we've got that slightly negative end, that slightly positive end, in other words, the dipole. And those dipoles will be attracted to each other. And now if we want to compare strengths of dipole interactions, because last year we just talked about it, now we want to ask the question, which then is the greater strength of a dipole? Then we need to look at the overall dipole. The more polar it is, the greater the overall dipole, the stronger the dipole force. And if the dipole force is stronger, then it should have a higher melting point, higher boiling point. And so now at this point, I'm on to the second page, which is going to have, which one is it? It's the one with BR2 and ICL on the bottom, because number 1 is on the bottom. You see the number 1 down there on the bottom. Because they don't tell you what order to put it in order to get it. Anyway, it's the photocopying thing. Okay, we got that? Everybody's moving? Here, I'll just advance it, and then you can see, right? That one, and it's on the bottom. It's on the bottom of one of those pages. Did we find it? Success? Same analysis. Go through exactly what you did before. Again, BR2, we've seen this already. Not that exciting. What type of molecule is this? It's nonpolar, they're identical. Total number of electrons, 70. And what type of intermolecular forces exist between two nonpolar molecules? London forces. So this is only London. Now this is ICl, all right? What we've done is we've taken an iodine and we've bonded it with a chlorine to do this type of thing. And now they're different. So when we look at type of molecule, I need to look at the delta En. So I need some electronegativities for iodine and electronegativity for chlorine. And you could just tell me the delta. I don't need to see both of them. What's the delta when you subtract the two? Yep. 0.5? 0.5. Even according to our new textbook, that would still fall right on the dividing line. We're going to use 0.2. So what does that make this thing? Yeah, it makes it polar. And you don't have to include the dipoles, but I'm thinking the chlorine has the higher electronegativity, right? It's closer to fluorine. So this one's going to be delta negative, and this one's going to be delta positive, just to kind of frame it with what we did yesterday. How many electrons does an I and a Cl put together have? 17 plus 53. 17 plus 53. And what is it? 70. Excellent. Now what that means is, and I'm going to just put this off to the side, this is good. When these two have the same number of electrons, we say it's isoelectronic. All right? We heard that term last year. It means the same number of electrons. So it's isoelectronic, which is good, because what's going to be true about the strength of the London forces? They're going to be equal. They're going to be the same, which means the only effect here that we're really seeing is the polarity effect. So what are the London forces? London. What types of intermolecular forces are taking place here? London and, yep, dipole, dipole. Dip, dip. So if we're going to put this in order of increasing boiling points, again, now we're picking boiling points instead of melting points. It doesn't matter. What's going to have the lowest boiling point of these two chemicals? Br2. Br2 less than ICl. Okay? And that's because it's only London forces holding together Br2, and it is London forces and dipole-dipole forces holding together adjacent ICLs, and therefore we have a higher boiling point. Any questions or concerns on this stuff? Okay, let's do one more, and then we will finish off today by talking about hydrogen bonding. Oh, sorry, no, two more. I got two more, just because the page has 2 and 3. Exciting. Again, go ahead and do the analysis. The analysis is pretty straightforward. I don't necessarily need 3D Lewis diagrams, but if you want to do them, that's great. It'll add to whether the dipoles cancel out or not. You do have to figure out whether it's polar or not. So something like H2S, that's like H2O, that's like water, except I've got an S in its position. sp3 hybridized with 2 lone pairs is going to make it bent. And then we've got an HCl. And again, where it says type of molecule, we need to determine some delta ENs. Now, I didn't make this table, and I've just been too lazy to change it. But if I were to do this, I'd put the delta En above the type of molecule, because that's going to tell you whether it's polar or not. So let's jump down to the delta En, and we'll find the delta En for these things. I guess I don't need to write delta En because it's in the delta En box. Again, I want it just for the S and the H. Yeah, what do you got? 0.38? 0.38. Now, we're going to go by 0.2. All right, folks, even though our textbook has for some reason wants 0.5, I got to investigate why they've changed that. We're going to go by 0.2, and if this is 0.2, what type of molecule have we got? Yep, yeah, polar. Have we got it for HCl? Has anybody done that calculation? Yep. 0.96, 0.96, and this is also polar. And have we totaled up electrons? You guys are pretty quick. You guys total up the electrons here. I'm going to grab the sheet. Sarah. We've already completed this one.
Okay.
And we are right there on that page right there, doing an analysis here. Total electrons. Sulfur, what is it, 16? 16 plus 2, what is that, 18? And Cl is 17 plus 1, 18. All right, excellent. So again, it's isoelectronic. They're going to have the same London forces. We can put that down here. London, London. They're both polar. Dip, dip. Dip, dip. And the question is, increasing boiling point. Well, this actually becomes a little more difficult than you might think. As I stated yesterday, in order to determine the overall polarity of a molecule that has more than one bond, we have to actually add up the dipole vectors to get the overall dipole, right? So in this case, we've got a dipole that heads towards this way and heads towards this way, and so the overall dipole is a combination of those two that cuts through there. And in this case, the dipole is heading over to the Cl and is just like that. And there's no easy way for us to calculate that blue dipole there, all right? Because you can't just take the delta ENs, turn them into vectors, and add them up. So for the simplicity of this course, when I ask you to analyze something like this, just look at the delta ENs, all right? It's an oversimplification, but it's kind of a beginning for you to say, okay, which one then is greater at being a dipole? And we're going to just look at the delta ENs and say that HCl is a stronger dipole than the HS. It's oversimplified. It may even result in incorrect conclusions if you were to do a Google search on the melting points. But for our purpose of analysis, because we don't know how to actually add these vectors up, we don't even know how to create the vectors because it's not as simple as getting the delta ENs. We're just going to use that. So for our analysis, because the electronegativity of the delta En of the HCl is greater than the delta En of the HS, we're going to say that the H2S, its boiling point is less than the HCl. All right, and I don't know why I drew a little structural diagram with that. You don't need to put the bond with that. Is that okay with everybody? That makes sense? It may be that it's the other way around, but for the purpose of you guys doing the analysis, that's the way we're going to do it. We're just going to look at the delta En. All right? And we've got one more to analyze. again, delta En, we just did the HCl. Can I go back while I get that running? 0.96 or something like that, wasn't it? 0.96. And you'll find once you get from, once you get from there to polar, you can jump down to here and you've got the London and dip. I don't know what this extra box here is for. I don't know why that's there. Again, I'm too lazy to delete it away. Total number of electrons, we did that as well. That was 18. Have we done an HBr delta En? What do you got? 0. Where is it? Oh, it's at the top of the page, of course. 0.76. 0.76 polar London and dip. Total number of electrons 36. 36 electrons. And which one do you think has the lowest boiling point? Well, I would say HCl. Okay? And that's the correct answer. We don't know here. Because if we're looking at London forces, there's going to be greater London forces in the HBr. And even though London forces are weaker, you might say, oh, there's more electrons, and the other one is dipole. It has a delta En of 0.96. This one should have the higher boiling point. But in the end, it turns out actually that increasing number of electrons really has a great effect, right? We say that London forces are weak, but iodine is a solid at room temperature, and it is only London forces that hold it together. So it is these electrons that keep the iodine molecules as a solid. This thing has 70 electrons, also just London forces, and it's a liquid at room temperature, like water is, right? Water is a highly polar molecule that's being held together by hydrogen bonding, and bromine is a liquid at room temperature that's just being held by London forces. So London forces can be just as strong as hydrogen bonds. So we can't just discount the London forces. So there's no way to predict whether the effect of the London forces will be greater than the effect of the dipole-dipole. So therefore, we cannot make a firm conclusion on this. So what are we saying? We cannot make a conclusion. Cannot predict or make a conclusion. We'll just put make a conclusion. Make conclusion. Right? And we'll put some reasons why. This is due to the fact that HBr has greater London forces, and HCl has greater dip. And therefore, it's hard to say. We can't make that conclusion. We don't have enough chemical knowledge in order to state and answer that question correctly. Okay? All right. Now, this is where in the past I've normally stopped and let you work, but because I've cut a lot out, I'm advancing faster than I have in the past, and it was really a dragging, slow lesson in the past. It was just painfully slow. So I'm going to keep going. And I want to next talk about hydrogen bonding. The reason I've kind of streamlined this lesson is because the last lesson, which talks then about properties of solids, I always find I'm rushing through that one. I need more time on that one. So it'll work out well. I'll be able to do the properties of solids lessons very thoroughly tomorrow and Monday. Again, still with review Tuesday and test Wednesday. This lesson used to take me 2 days, and then I would rush through the last one. And the last one's actually more important than this lesson. This is super review. If you're going to watch the movie, Sarah, what I might do is because of the interruption with all of we had interruptions with the candy canes, I might leave up last year's version of it. It's just going to have more words on the slides. You won't need to write it all down. If you get the notes from somebody, then all you'll need to do is listen to the analysis that I did.
Okay.
Yeah, but we've had lots of interruptions. I could edit it away, but we'll see. We'll do it later maybe. Okay, hydrogen bonding. Again, we've talked about this last year. If you've got a hydrogen bonded to a highly electronegative atom, nitrogen, oxygen, fluorine, it results in a very large delta En and a very large overall dipole. Hydrogen bonds are much stronger intermolecular forces than London and regular dipole-dipole forces and tend to have much higher melting points and boiling points.
So it's an electron, it's like a molecule has more electrons,
Mm-hmm.
but the other one has hydrogen bonding.
Mm-hmm.
Say that the one with more electrons is the lower one.
Again, it becomes one of those inconclusive situations. We don't have enough information with that. Hydrogen bonding, though, is quite strong. So are you asking, do we have hydrogen bonding trump the more electrons? Again, I would say it's inconclusive. The effect of the electrons are greater than one would think, because we always teach that London forces are the weakest. But it doesn't take much to get us to a liquid at room temperature, something like octane, which is the main constituent of gasoline. C8H18 again has numbers of electrons that are comparable. Goodness, I'm trying to compare it to something, and I'm not ready. I don't even have an example. But those are liquids, right? They're liquids at room temperature, so those forces have to be strong. Now, hydrogen bonds, you're kind of jumping ahead on me here, but that's okay. Hydrogen bonds, though, are very, very strong, because if I were to look at water, and water is the classic example, you've kind of beaten me to the punch here, but that's fine. If I were to add the number of electrons up in this, I'm dealing with 8, 9, 10 electrons, right? There's 10 electrons in water, and we were looking at CH4. What's in CH4? 6, 10 electrons? 10 electrons, right? This is methane gas, right? This is, what comes out of our taps here. And it's very difficult to liquefy it. You have to have it like super, super cold. You have to have it, minus 150 degrees Celsius. You've got to compress it, and you've really got to squeeze the heck out of it in order to liquefy it. Where water, just at room temperature, is a liquid. So the hydrogen bonding in this is a massive effect. Something with 10 electrons has no business being a liquid at room temperature. So hydrogen bonding does have a great effect in that. But if I give you one that has that electron imbalance and hydrogen bonding, probably an inconclusive situation. That'd be and I would accept it. Your logic would be fine. Yeah. Okay? All right, let's look at some examples here. Oh, this is just some biological examples of hydrogen bonding. Again, the teacher who made this PowerPoint, and I'm editing from it, thinks that there's a lot of important biological things taking place with hydrogen bonding. So I just, leave them in there. Anyway, many, protein type things are hydrogen bonded together, like in silk. DNA, again, someone told me that's important in some way. I don't know, it has some kind of significance. But the hydrogen bonds, again, if we look at all these, what do we call these little guys in here? What are the amino acids or something? Come on, biologists. What are in the DNA? What holds them? What is it? What are they? They're amino acids?
Phosphate, sugars. Nucleotides, the whole thing.
I didn't understand a thing she said. Anyway, someone told me that the double helix is held together with hydrogen bonds. That's important. No? Yes? That's all I got. That's as biology as it gets. Okay, so let's take a look at some of these. Hydrogen bonding is very significant in biological systems. Again, we do the same analysis. Oops, I was going to write with chalk on that thing. That wouldn't work very well. Oh. Delta En, I don't remember. Oh, it was 0.3 something for the HS. We've seen H2S, haven't we? 0.38, therefore it's polar, therefore it's London, and this is not one of our O, N, or F, so this is dip. And is it 18 electrons for this one? No. Is it? Yeah, 18 electrons. Yeah, because I just did the water. That's 10 electrons. And you know what? This is one where is exactly. You already looked ahead. That's what you did. You finished the work ahead. Oh yeah, okay, that's all right. You see, and we know that water is the liquid here. What do we got? 0.96. What was it? Oh no, sorry. I was thinking of. Yeah, I was thinking of HCl. 1.24. 4. Then this is H bonding and London. And you know what? If you were to make the argument that it's inconclusive, I guess I'd give it to you. But this is hydrogen sulfide. This is a gas. I know that from just what I know. And this is obviously a liquid. And, yep. Because this delta En is not strong enough. It has to be O bonded to H. It's the thing the H is bonded to that determines whether it's H bonding. It's not the H. It's the fact that the H is bonded to an oxygen, which makes this thing really big, which makes it H bonding. Okay? Yep.
So when we're doing our solution, figure out what phases and temperature and then.
Well, that's then cheating. That's using empirical information to tell you the theory, right? What we're really getting across here is that I'm trying to just introduce you to the factors, but it's far more complex, right? You need to learn more in order to get the complexity. If you were to put on a test inconclusive because one has more electrons and the other one has H bonding, I would say, yeah, that's good. I'll give you that. In reality, in this case, though, the melting point for H2S is less than H2O. All right. So if you were to do the argument, that's great. I would give it to you. And in reality, this is a gas and this is a liquid, and this is due to the H bonding. All right. So as scientists, we're then contributing that to the H bonding. Now, at some point in time, at some point in a comparison, I guess in theory, I'm not sure, it would be interesting to see what something like tellurium with 2 H's on it would be. Polonium is radioactive, but it does exist long enough. I wonder what polonium with 2 H's would be. When I'm done the lesson, maybe I could go back and check, right? And you might see that at some point in time, we do get them being as liquids or solids because of the electron effect. But this effect obviously isn't big enough. There's no way for you to know where or when that does that unless we were to actually get the real data, and then we could say, okay, so this many electrons obviously can override the hydrogen bonding effect. I'm not worried about that here in this course. I just want you to think critically and argue logically. Okay? So let's take a look at those. And actually, you guys go ahead and analyze that. And I'm going to check I want to check these. I'm going to check them online just for a moment to see what we get for like SEH2. So SEH2, its melting point is negative 65.73. Negative 65.73. SH2 has a boiling point of negative 60. This is a melting point. Negative 60 is a boiling point. They don't even show a melting point. Water obviously has a melting point of 0. Come on, let's finish this off, folks. Or are you already done? It's giving me boiling points. Oh, melting point of hydrogen telluride, negative 50. Negative 50. So you'll notice the electron effect has not even come into play, even close to it. That's a boiling point, which means its melting point's much colder than that. We're getting to negative 50. The hydrogen bonding seems to dominate greatly. Well, we've only got one more choice, PO. Very unstable at room temperature. They do. One of them quotes a melting point of negative 36, which means it never dominates over the hydrogen bonding. The hydrogen bonding dominates, and you could say that. From what I just checked quickly, you could say that the hydrogen bonding is going to dominate. Yeah. Yep. Okay. Is this our last one? Or is there one more set of boxes on that last page? Just this? Or one more? Okay, Lewis structure. C. What's going on? Oh, I got it frozen. Thank you very much. Very much. Again, I don't need 3D at this point. Hard to draw that. 1, 2, 3, 4. 1, 2, 1, 2, 1, 2, 3, 4. I'm going to just leave the H's off of that thing. What type of molecule is this? Non-polar, right? It's all C's and H's. Total electrons? Sorry, 34? 34 electrons. Delta En, I'm not even going to worry about that. Intermolecular forces, London. CHH, Cl. Because of the Cl, the symmetry is broken, all right? And this ultimately becomes polar. You could calculate the delta En for both the CH and the CCl bonds, but don't worry about it. They're all going to come this way, right? The electrons are being moved towards the Cl. Total number of electrons? 26? 26 electrons. And here we've got CHH and HH. I don't know why I added those H's this time. Okay. Lone pair. Again, due to the N, again, you can calculate the delta ENs, but due to the N, it's going to be polar. The N bonded to the H. Do we have the total number of electrons? 18. 18 electrons. And this is going to be London and dip-dip. And this is going to be London and H bonding. And you know what? This I know is a gas. I'm not sure what the state of this thing is. That's a gas as well. I'm going to say for this course, if you've got hydrogen bonding, let's have it dominate out of it, right? Let's do that because it seems to be the evidence here. Yep. If you've got hydrogens bonded to a carbon, all right, they are little dipoles. In this case, they cancel out. In this case, they don't cancel out. In this case, they will contribute to the polarity, but we would not say that this end participates in hydrogen bonding. This end will hydrogen bond with another molecule that's just like it, with that end again, with the H's that are coming off of the N. All right? So I would have another molecule where these two H's are being attracted to this N side. That's what makes the hydrogen bond. Okay? All right? No, you don't. No, you don't write dipole-dipole. You just write H bonding. Yep. And so we're going to then say the lowest is the London, C4H10, less than CH3Cl, less than CH3NH2. And again, this one due to H bonding. All right? Then those molecules can participate in hydrogen bonding, and they will have an increased melting point or boiling point. And you guys are writing away already, which is excellent, so I'll just catch up with you here. Doesn't have to be 3D. I think we, even without calculating the delta En, all understand that, yes? Yeah, it makes it ionic, you're right. You could put ionic there if you'd like. But but it is still molecular. It's one of those guys that is technically still a molecule, even though it falls under that definition of what is ionic. If you were to put ionic there, that'd be fine. Yeah. Total number of electrons. Sorry? Are they? 10, 10, 10. Isoelectronic, which means we don't have that in our way. And these are all nitrogen, oxygen, and fluorine. So London and H bonding for all of them. And so if we're going to increasing, what would have the lowest here, do you think, on our prediction? Oh, you know what we need? We need the delta ENs then, don't we? Because they're all kind of the same. Which one's the strongest ones? So what's the delta EN here? Have we got that number? 0.84, 1.24, 1.78. So which will have the lowest melting point or boiling point? NH3? NH3 less than? Yep. Yeah, H2O. Less than? HS. Now, I do have a couple more slides, but I will do a little review and we'll finish it off tomorrow before we move on. And you don't have to write this down right now, but you are going to need to write this down, folks. It turns out that the actual ranking, when you actually look up those melting points, boiling points, again has water as being the highest. It turns out that HF is actually the lowest, and the NH3 is in the middle. It's exactly opposite to what you'd think. And again, that illustrates that our simplistic representation is really just a very simplistic introduction. It has to do with the fact that water's bent shape allows the two hydrogens on adjacent waters to get really close to those oxygens. And it allows that H bond to be that much stronger because of multiple interactions, all right? And it also packs very nicely. The way it packs together is very significant. So again, water is a very significant molecule in the way in which it bonds. I'm going to bring this back up. If you don't get it all down, you're trying to right now, I'm going to start with this slide tomorrow, and we'll finish off a couple of slides that just kind of bring this all together. You have that worksheet. You can do all of the questions on that worksheet. A lot of it involves the exact analysis that we did. You're going to break it into this and that, and count up electrons and compare. The very last question is a question on solubility, and that's because I used to do the solubility little piece of a note right now, but I did that yesterday, so you already know the solubility note in order to answer that. We will stop right there. How quickly can we get into test configuration? Can we do it quickly? Can we do it in the next minute? It'd be great if we could do that. You don't have to push anybody over.